Welcome back to Polynomial Functions. Today we're going to be finishing everything off. So we're looking at graphing polynomial functions today. And in order to kind of kick this off, we're going to look at how to make sine graphs. You might have used sine graphs, that's S-I-G-N sine, not S-I-N-E sine. You might have used them to solve quadratic inequalities. So if you had something, for example, like x squared minus 2x minus 8 is greater than or equal to 0, if you needed to solve that, well then you might have set up essentially a modified number line where you looked at the value of x and you looked at the value of f of x, and then using your knowledge of what the zeros were for that function kind of built this thing. So noting that f of x itself is like x minus 4 times x plus 2, we can note that this would be solved when x minus 4 is 0, so that's at positive 4, and when x minus 2 is 0, so negative 2. We can say that our critical values are 4 and negative 2, and plot that on this number line, where we've got negative 2 and 4. And what we're noting with this sine graph is that when x is negative 2, f of x is 0. When x is 4, f of x is 0. And then for these other sections, we're either saying that they're positive or negative, depending on what's happening. Our knowledge of quadratics and how they operate allows us to note that this particular one would be upward opening, and that its ends would be positive, and in the middle, it would be negative. Take a moment, make sure you can fill out the other ones, see what's going on. I'll do some minor explainy-doos as we go through these, but do make sure that you are familiar with getting these sine graphs before moving on. Over I go here, this thing is just x plus 3 squared. So we've only got one critical value, and that's at negative 3. Plotting this thing, here's x, here's f of x. There's only one critical value. When x is negative 3, f of x is 0. And this thing being upward opening again, because that positive lead means that we're positive at each end. Over to this one, x squared plus 4, it's not factorable, first of all. If you use the discriminant, then you can find that it has 0 x-intercepts. Or you can picture what this looks like as a graph, right? Where here's x squared, so there's x squared plus 4, that upward shift. But in any case, we note that this has no critical values. So when we look at its sine graph, or sine diagram as some call it, there's nothing placed here, there's no numbers. We just note that this one, again having that positive leading coefficient, is positive the whole way through. Finally, for this last one, this thing factors a little bit, plus 5x minus 36. So the negative of x plus 9 and x minus 4, telling us that we have critical values at negative 9 and positive 4, thus allowing us to draw our sine graph where we have zeros at negative 9 and 4. And this one being a downward opening parabola, we know it's negative on the ends and positive in the middle. So looking at this, we had some options. When we worked with quadratics, we noted that they could have 2 zeros at most, but they could also have just 1 0, or they could have no zeros at all. Something that had 2 zeros, we would note that these factors each had a power of 1 and switched signs, and the graph switched signs over that particular factor, right? That's the graph saying, oh, I've hit negative 4, I'll go into negative land, or a negative 2, go into negative land. And then when it hits 4, whoop, go back into positive land. That's what happens there. And we compare that to a situation like this, where the 0 is at -3, and that's the case where we reach that 0, and then instead of going through, we bounce back up. This kind of leads us to the concept of multiplicity. So the multiplicity of this 0 we can say is 2. And because its multiplicity is 2, it behaves a certain way. In this case, again, recognizing that it just kind of bounces back. The multiplicity of these zeros is 1 because they're each in there only once, to the power of 1. And that's what causes them to behave in the ways where they just cut through and cut through again at the other end. Wait, that's a highlighter. So when we talk about multiplicity, we can say that if a polynomial function has a factor like that, that's repeated n times, then a is a 0 of multiplicity n. Do note there I did make a little typo here. Somebody forgot to hit shift when they went for the plus sign, so that should say x plus 3 squared. Anyhow, moving on. So what that says is if you've got a factor and maybe you have like x minus 6 to the power of 9, then 6 is a 0 with multiplicity 9. We've got an example right here where I'm drawing and taking up valuable real estate. And we're going to list the zeros of this function, and we're going to state the multiplicity of each one. So the particular 0 and its multiplicity. I encourage you, of course, to take a stab at this. See if you can take that definition and work with what we've got. See if you can determine the zeros of this function and the multiplicity of each. I, of course, will be doing so right now. So one of those is what makes this thing equal to 0. 0. So if x is 0, then this is 0, making this whole product 0. So there you have it. The multiplicity of that is right up here, so that's 2. Our next one is coming from this factor. What makes that factor equal to 0 is -1. The multiplicity of it, well, its exponent, it's invisible, but we know it to be there. It's 1. Then we've got this factor. What makes that factor equal to 0? Well, it's +1. And its multiplicity is right up here. That's 3. And then our last factor is x plus 2. What makes that factor 0? Well, that would be when x is -2. The multiplicity of that is just 1. The behavior we get based on the for a particular 0 is based on that multiplicity. That's just as we saw up here when we had a multiplicity of 2, a certain behavior, and a multiplicity of 1, a certain behavior. So if we have a multiplicity of 1, we're going to note the function kind of just cutting through. It's going to resemble something kind of like this. Or if it goes from negative to positive, maybe it'll resemble something kind of like this. And it might be just really small scale. It might just be a little bit, but it's going to be a cut through. So it's not necessarily going to be whoop forever ever like that, but it cuts through very straight. If we have a multiplicity that's even, so multiplicity of 2 or 4, 6, 8, then we're going to see a little bit of a bounce back. So it's going to curve in to that x-axis, and then it's going to curve back out. And maybe it'll do it up like that, or maybe it'll just do it in negative land. So it reaches the axis and then backs away from it. And then finally, if we have an odd multiplicity other than 1, it's going to go through, but it's going to wiggle a little bit. So maybe we go from positive to negative, so it's going to curve into that 0, and then say, you know what, I'm going to keep going here. Or going from negative to positive, same thing. It's going to come up here, it's going to say, oh, I'm going to approach a 0 real gradually. And maybe it'll bounce back. Psych, I'm going to go through. So those are what the graph will look like at that 0. Now we're going to be using this information to put everything together and graph polynomial functions. Before we do that, let's just take a moment to graph some other sine diagrams. So just as we did these ones for quadratics, we'll do this for higher order polynomials. As we do this, we establish our critical values. Critical values are still just the zeros of the function here. So the critical values in this case are 3, -5, and 1. And now we can make our sine diagram. We've got -5, we've got 3, we've got 1. This doesn't have to be to scale. We just need to have them in order and identified. So on the bottom we have our values of x. On the top we have the behavior of f of x. Noting that when x is -5 or 3 or 1, f of x is 0. So in the question for each of these is this positive or negative? Positive, negative, positive, negative. Who knows? There's a number of ways we can play with this. So for starters, to kick this thing off at one end or the other, we can note that the leading coefficient is positive. And the degree of this thing is what? Oof. Well, we've got an x squared. That'll get multiplied by x. That'll get multiplied by x cubed. So when we multiply those all together, we get x to the power of 6. That'll be the highest exponent we see. So knowing that it's got a positive lead and an even degree means that both ends will be positive. A couple ways you can interpret that. One is that since the leading coefficient is positive, this must end positive. And the other way is, and along with that, is that since it's got an even degree, both ends must be the same. So there's that. But what about this stuff in here? What happens? Well, let's know what the multiplicity means again. So if it's got an odd multiplicity, it will switch from positive to negative or negative to positive. Same over here, negative to positive or positive to negative. One of those, try again. Positive to negative or negative to positive. So that will happen, and it will change sign over that 0. But if it's even, it'll go from positive to positive, that looks like a smiley face, or negative to negative. So it won't change sign over an even multiplicity, but it will over an odd. So looking at this one, as we hit -5, we know -5 has odd multiplicity, so this function will change signs. Instead of being positive, it'll cut through and go into negative land. As we hit 3, we note 3 has an even multiplicity, which means it'll be doing either this positive to positive or negative to negative. Well, since it's negative here, it must then be negative there. So it does not switch over the 3 because of its even multiplicity. And finally, just to confirm, this 1 has an odd multiplicity, and it's not 1, so it's going to do like a wiggle through, either wiggle that way or wiggle that way. But it's going to change signs, and it changes from negative to positive, so this is all good. Try the others on this page, and then we will sketch these things like you wouldn't believe. Oh, here I go. We've got some critical values. Let me see, 0, -7, -3, and +3. And if I want to note the lead, this thing has a positive lead, and degree, I'm getting 1, 2, oh, that's 5. That's 5. This is another 2, it's another 1. So 1, 6, 7, 8, 9. Is that correct? 1, oh, whoops, this is degree 4. I know how to count. There we go. This thing's 8. So now I can make my sine diagram. X, f of x. Listing things in order. There we are. F of x is 0 at each one of those values. They are the zeros of the function. The lead is positive, so I'm finishing positive. The degree is even, so both sides should be same. Okay? Over -7, even multiplicity, I'm not switching. Over -3, even multiplicity, I'm not switching. Over the 0, odd multiplicity, I'm switching. And over 3, odd multiplicity, so it switches again. And that one's done. Over here, critical values include, what is that, 2/3, -7/4, -6, and 2. The lead of this one, now, I mean, do be careful a little bit, pay attention to what's in these brackets, but the lead will come from the leading coefficient within each factor. So what the actual value is will be 3 to the power of 1 times 4 to the power of 9 times 1 to the power of 1 times 1 to the power of 10 times -4. For now, what I'm doing, for the purpose of getting the sine diagram, I don't need its value, but I do need to know if it's positive or negative. And in this case, we'll have a positive value, because it's positive times a positive value times a positive value times a positive value times a negative value. So this lead is negative. And then degree, we've got 1 plus 9, which is 10. We got 11, and then another 10. So this degree is like 21. Whew, what a doozy. Well, let's put this thing together. X and f of x. So from least to greatest, -6, -7/4, 2/3, and 2. And f of x is 0 at each one of those. Negative lead means I'm finishing negative. Odd degree means that they are opposite at either end. And now for the in-betweens. 6 has a multiplicity of 1, so we switch over it. -7/4, that factor is giving us multiplicity of 9, so I'm switching over that. 2/3 comes from something that has a degree of a power of 1, so we're switching over that. And then 2 comes from something with an even multiplicity, so this stays same. Everything seems to be in order. That is done. So let us graph some functions. When we do so, personally, if it's not factored, you'll want to factor it. If it is factored, then we can jump to making this sine diagram, and then you might want to actually draw in the multiplicity, like what the graph might look like around each 0, and then we'll put everything together. When we do, we should label everything that we can. We should have a scale for the x-axis so that we can identify what the values of each x-intercept are. And then we'll just need one tick mark for the y-axis, and that'll be where the y-intercept is. So here we go. Critical values of this thing are at 2 and -5. Oopsie daisy. Sine diagram. You should be making sure you can get the sine diagram on your own. I'm about to do it. Noting that this thing will end positive. It should be same on either side of the 2. and it should switch for the negative 5. That's my sine diagram. One thing we haven't gotten yet is y-intercept, so let's quickly get that. And that happens when x is 0, so we've got negative 2 squared times 5 for a value of 20. We put it together. So let's get some tick marks up in this business. 1, 2, sure. I don't need nearly as many as I've got on that side. And I'm covered on that side now too. All right, so at negative 5 we have multiplicity 1, and we go from negative to positive. So what we'll see at negative 5, 1, 2, 3, 4, 5, is us going from this negative land to this positive land, and it'll be a very straight cut through it. I think there'll be a slight curvature to it, but no kind of wigglies. It'll cut right through. And when we hit 2, that's got an even multiplicity, so that's where it's going to do that bounce back this way or this way. We're going positive to positive, so we'll go positive to positive. Now we're going to kind of play connect the dots, except we're playing connect the pieces. So this thing will go up for a bit, but at some point, we don't know where. We're not taking calculus, but at some point it'll start going back the other way, and that'll allow it to connect to this other piece. On the very left side, it's just going to continue towards negative stuff forever. On the right side, it's going to continue upward towards infinity forever. And now we can do some labeling. So that's really thick. That's 2. I mean, we could label the 1 if you want to, whatever you want. This right here is our y-intercept. That happened at 20, if I'm not mistaken. And then, of course, our axes. This is x, and up here is y. This thing is graphed. We can see how it matches with our sine diagram, that we go from negative to positive to positive. Right? So we're negative, then we're positive, and then positive again. So that's how it all matches up. Feel free to try the other ones. There's 2 more examples of graphing, and then 2 examples of finding the equation from the graph. But give them a try and see what you can do. And I go, my critical values in this case are negative 4 and 1. Negative 4 and 1, and that's for x versus f of x. This whole thing is going to end negative, okay? And then over 1, it's going to switch because of that odd degree. And over 4, it's going to switch again because this is odd as well. Okay. And then y-intercept. F of 0 is the negative of 4 cubed times negative 1. 4 cubed is like 64. So that's that. And we can put this thing all together. We'll need some tick marks on our graph. And as we hit negative, let's go with the 1. 1 goes from positive to negative, and it's a straight cut through. So there's kind of what we're doing at 1. All right. And at 4, we're doing kind of a little wiggle dance. We're going from negative to positive. but we're wiggling through it because of that 3. So instead of cutting straight through like that, we're going to come up and curve in and then curve out. And now we play connect the pieces. If we go up a bit, at some point it's going to have to curve back to meet up with our function at the other end. Whee! And then, of course, to infinity and beyond, over here and over there. And by infinity, of course, that's negative infinity, as we can tell by our negatives there and there. I should label this at some point. That's 2. This intercept is happening at 64, I think it was. And then, of course, just our axes. There's y, there's x. And then, last example. Our critical values are at 0, 4, and negative 2. So we've got negative 2, we've got 0, we've got 4. F of x is 0 at each one of those. This has a positive lead, so I'm finishing positive. Over 4, we don't change. Over 0, we do. And over negative 2, we do. Y-intercept is, 0 cubed times negative 4 squared times negative 2 is 0. Okay. Now let's graph this. I actually want to space this out a bit more. If I've got the room, I might be able to use it. It's 1, 2, 3, 4. 1, 2. And make sure these are like decently evenly spaced. You don't want to be doing something like, if this is your line, being like, okay, there's 1, there's 2, there's 3, there's 4, there's 5, there's 6, there's 7. Like, no. That's just like I'm reading I don't know, some sort of chart. All right, how does this thing dance? At negative 2, that's a straight cut through from positive to negative. So at negative 2, you kind of cut through straight from positive to negative. At 0, we do a little negative to positive, but with a little wiggle dance. So from negative to positive. And then at 4, we go positive to positive. Oops, I'm good. 1, 2, 3, 4, so positive comes in and then goes to positive. And now we're going to connect all these. There's that. And up this goes forever that way. At some point, this is going to have to swing back down and hit that. And then, of course, at the other end, just upwards forever and ever. Hooray! So that's done. We do have 2 more examples left on this next page. Oh. I forgot to label my everything. Don't forget to label the axes. Don't forget to label the scale. So that's that. On the next page, just 2 more examples left. Thanks for bearing with us here. We're going to determine the equation of some graphs. So, in doing so, what we're going to note is each 0 that we have. So every x-intercept that we have will give us a 0 for the function. And then we can determine the lowest possible multiplicity for each one by noting its behavior at that 0. We'll also have to try to figure out a coefficient for the whole thing, kind of like, where are we? This one had a coefficient of -1, and we had some other one here that had this one had a coefficient of -4, like a multiplier just outside everything, this one with a 3. So what value is that going to be? We're going to do that by using the Y-intercept. So we know that for this function, we have to include, at the very least, an x plus 1 because of this 0, and that has to be of an even degree. So we'll at the very least 2. We also have to have at least an x minus 2, and that cuts right through, so that'll be to the power of 1, and similarly an x minus 3 to the power of 1, because it's not like it's wiggling through, it's just cutting straight through. So we have to have all that. So when we put our function together, we could say y equals some value being multiplied by x plus 1 squared times x minus 2 times x minus 3. That's the beginning of it. In order to figure out this value, we'll use the y-intercept, which is at 3. So we can say the y value is 3 when x is 0. So we've got 0 plus 1 squared, 0 minus 2, 0 minus 3. And then we'll just calculate this. We'll solve for a. 3 is equal to a times 1 times -2 times -3. So 6a. A must be 1/2. And putting that together for our final answer, y equals 1/2 of x plus 1 squared, x minus 2, x minus 3. Try this other one. Give it a go. See what happens. Obviously, I'm going to jump in, but you have the ability to pause. Use those pausing skills. So we must include here an x plus 1 to the power of 1 and an x minus 2 at least to the power of 3. I don't know, like it could be a 5, it could be a 7. I know it has to be odd, and that since it's wiggling through and not just a pfft, that it has to be 3 or higher. So it can't be multiplicity 1. Okie days. So y must be some value times x plus 1, x minus 2 cubed. Our intercept is at 8. So 8 is a times 0 plus 1, 0 minus 2 cubed. That's what I got there. And a must be -1, which allows me to say for this function, I've been saying y equals, if you use f of x here, then you can use f of x there. Either is acceptable. But y equals negative x plus 1, x minus 2 cubed. And that is done. And there are other final checks we can do just to make sure. It's a good thing that we got a negative leading coefficient out of this, because this finishes off negative. It goes off to negative land. So we better have a negative leading coefficient for that. But that's that. There is some practice work here, of course. Give it a go. It is very useful, but also useful are the provincial questions. So you got your textbook review because we're at the end of the topic. But the provincial questions from January 2019 are worth a look. 5 questions out of 49. They made up 10% of the final exam that year. So certainly something that warrants examination. So try those. Make sure you're comfortable. And don't forget to check out the provincial exam archives and that questions list provided to you. And of course, if you have any questions, comments, concerns, please feel free to reach out. Let me know. the easiest way for me to answer your questions is for me to know what they are. So provide me that information, and I shall provide you with information in turn. That is all. I will see you in the future. Tell everyone I say hello, and have a good rest of your year. Woo!